So here's something worth thinking about as you settle in tonight. Right now, wherever you are, you're sitting at the bottom of an ocean. Not an ocean of water, an ocean of air. It stretches about 100 kilometers above your head, give or take. This thin shell of gases, clinging to a ball of rock, hurtling through space at about 107,000 kilometers per hour. And when I say thin, I mean shockingly thin. If you shrank the Earth down to the size of a basketball, the atmosphere would be thinner than a coat of varnish. That's it. That's all there is between you and the cold vacuum of space. A whisper of gas, a smear of molecules, and everything. Every breath you've ever taken, every storm, every sunset, every climate you've ever experienced, all of it happens inside that paper-thin layer. And that layer is doing something extraordinary right now. It's keeping you alive. Not just by giving you oxygen to breathe, though obviously that's important. It's keeping the planet warm enough for liquid water, for life, for all of it. Without the atmosphere doing what it does, the average temperature of Earth's surface would be about minus 18 degrees Celsius. That's roughly 0 degrees Fahrenheit, below freezing, everywhere, all the time. The oceans would be ice. Life as we know it simply wouldn't exist. But instead, the average surface temperature is about 15 degrees Celsius, roughly 59 Fahrenheit, which is comfortable, livable, miraculous if you think about it. And the difference between that frozen wasteland and the world you live in, that 33-degree swing, comes down to something that took humanity centuries to figure out. Something so subtle and so fundamental that it underlies nearly everything we're going to talk about tonight. It's called the greenhouse effect, and despite what that name might suggest, it has very little to do with actual greenhouses. But we'll get to that. Tonight we're going to talk about climate, all of it. What it is, how it works, how we figured it out, how it's changing, and why it matters. We're going to take the whole thing apart, slowly, from the very beginning, and we're going to walk through it together. No rush. This is the kind of subject where every layer you peel back reveals something more interesting underneath, and some of those layers go very deep, so just settle in. If you drift off at some point, that's completely fine. The atmosphere will still be there in the morning, doing its thing. It's been at it for about 4.5 billion years. It's not going anywhere. Let's start with something basic. What is climate, actually? Because people mix up climate and weather all the time, and they're really not the same thing. Weather is what's happening outside right now. The temperature, the humidity, whether it's raining, what the wind is doing. Weather is immediate and local and chaotic. It changes hour by hour, day by day. The weather forecast for next Tuesday is a best guess, and honestly, it might be wrong. Climate, on the other hand, is the long-term pattern. It's the average of weather over decades, over centuries, over millennia. Climate is the reason you expect summers to be hot and winters to be cold. Climate is the reason the Sahara is a desert and the Amazon is a rainforest. If weather is your mood on any given day, climate is your personality. Weather is the individual hand of cards you're dealt. Climate is the odds built into the deck. And the thing that determines those odds, the thing that sets the fundamental rules of Earth's climate, is energy. Specifically, the balance between how much energy the planet receives from the sun and how much it radiates back into space. That's it. At the most basic level, that's the whole game. Energy in, energy out. If those two numbers are equal, the temperature stays stable. If more energy comes in than goes out, the planet warms up. If more goes out than comes in, it cools down. Everything else, the winds, the ocean currents, the seasons, the ice ages, the droughts, the floods, is ultimately downstream of that energy balance. And understanding how that balance works, what controls it, what can knock it off kilter, That's the story of climate science. And it starts, like so many great stories in physics, with a French mathematician who was mostly interested in heat. His name was Joseph Fourier, born in 1768 in Auxerre, France, a small town in Burgundy. And Fourier's life story is one of those ones that makes you realize just how tangled science and history really are. He was orphaned by the age of 10. He grew up during the French Revolution, actually got arrested during the Terror, came close to the guillotine, and was saved only because Robespierre himself fell from power before the execution could happen. Fourier later joined Napoleon's expedition to Egypt in 1798, helped establish the scientific institutions there, and eventually returned to France, where he became a prefect and a serious mathematician. The man lived through revolutions, wars, and political chaos, and somehow, through all of it, he kept doing math. And here's what matters for us tonight. In the 1820s, Fourier was working on the physics of heat, how it flows, how it conducts, how objects reach thermal equilibrium. He'd already done groundbreaking work on what we now call Fourier analysis, this mathematical technique for breaking complex waves into simple components, which turned out to be one of the most useful mathematical tools ever invented. It's used today in everything from signal processing to MRI machines to JPEG image compression. But that's a side note. The important thing is that Fourier understood heat better than almost anyone alive, and he turned his attention to a question that seems almost obvious once you hear it, but nobody had really tackled properly before. Why is the Earth as warm as it is? Fourier knew how far the Earth is from the Sun. He could calculate how much solar energy reaches us, and when he did the math, something didn't add up. Based on the solar input alone, the Earth should have been significantly colder than it actually was. Something else was happening. Something was trapping heat. Fourier proposed, around 1824, that the atmosphere itself must be acting as a kind of insulator. He compared it to a glass box. He actually used the analogy of a box with a glass lid that lets light in but traps the warmth inside. This is where the term greenhouse effect eventually came from, though Fourier didn't use that exact phrase, and the analogy isn't quite right. A real greenhouse works mainly by physically preventing warm air from rising and blowing away. It's a convection trap. The atmospheric greenhouse effect works differently, through radiation, which we'll get into. But Fourier's core insight was correct. The atmosphere lets sunlight through, but impedes the outgoing heat radiation. Something in the air is catching the heat on its way out and sending some of it back down. And that's why the surface is warmer than the raw solar calculation would predict. Now, Fourier didn't know which gases were doing this trapping. He couldn't. The experimental tools didn't exist yet. He just knew something in the atmosphere was responsible. And that question, which components of the atmosphere are actually trapping the heat, would take another 35 years to answer. And the person who answered it was a fascinating Irish physicist named John Tyndall. Tyndall was born in 1820 in Leylandbridge, County Carlow, Ireland. He came from a modest background. His father was a local police constable, and he worked as a surveyor and a draftsman before getting drawn into science. Eventually, he made his way to the University of Marburg in Germany, got his doctorate, and came back to England, where he became a professor at the Royal Institution in London. And he was a character, a mountaineer who made first ascents in the Alps, a gifted public lecturer, a man who could explain complex physics to a room full of non-scientists and have them genuinely enthralled. He was one of those rare people who combined serious experimental talent with a real gift for communication. And in 1859, Tyndall set up an experiment that would change how we understand the atmosphere forever. He built a long tube, sealed at both ends with plates of rock salt, because rock salt, unlike glass, is transparent to infrared radiation. and he filled it with various gases, then shone infrared radiation through the tube using a heated copper cube as a source, and measured how much radiation made it through. He used a device called a thermopile to detect the radiation on the far end, and his measurements were extraordinarily sensitive for the time. Tyndall was a gifted experimentalist, the kind of person who could coax meaningful data out of apparatus that in someone else's hands would produce nothing but noise. And what he found was remarkable. The main components of the atmosphere, nitrogen and oxygen, which together make up about 99% of the air you breathe, turned out to be essentially transparent to infrared radiation. They don't absorb it. Heat radiation passes right through them, as if they weren't there. But the minor gases, the ones present in tiny, tiny quantities, those were a different story. Carbon dioxide absorbed infrared radiation powerfully. So did water vapor. So did methane, and nitrous oxide, and ozone. These gases, present in amounts measured in parts per million or even parts per billion, were doing almost all of the heat trapping. Tyndall had found the specific culprits, and he immediately grasped the significance. He wrote that, without water vapor and carbon dioxide in the atmosphere, the Earth's surface would be held fast in the iron grip of frost. He understood that these trace gases were the reason the planet was habitable. Think about what that means for a second. Nitrogen and oxygen, the gases that dominate the atmosphere, the ones you're breathing in and out right now, they're essentially irrelevant to the temperature of the planet. They don't interact with heat radiation at all. The entire greenhouse effect, all 33 degrees of it, the whole difference between a frozen wasteland and the world you know, that's all being done by gases that make up less than 1% of the atmosphere. Carbon dioxide is currently about 0.04% of the air. 400 parts per million. That's it. And that tiny trace is one of the primary thermostats of the entire planet. It's as if the whole climate system is balanced on a razor's edge, exquisitely sensitive to these minute concentrations. And in a way, that's exactly what it is. Now, let me explain how this actually works, the mechanism, because it's elegant and it's important, and you don't need a physics degree to follow it. Sunlight arrives at the top of the atmosphere. It's mostly visible light, the kind of light your eyes can see, along with some ultraviolet and some near-infrared. The atmosphere is mostly transparent to visible light, so most of the sunlight passes right through and hits the ground. The ground absorbs it and warms up. So far, so good. But here's the key. When the warm ground radiates energy back upward, it doesn't emit visible light. It emits infrared radiation, heat radiation. And the wavelength of that infrared radiation is longer than the wavelength of the visible light that came in. This is just basic physics. Cooler objects radiate at longer wavelengths than hotter objects. The sun, at about 5,500 degrees Celsius on its surface, emits mostly visible light. The Earth, at about 15 degrees Celsius on average, emits infrared. Different wavelengths, different parts of the spectrum. And this is where the greenhouse gases come in. They're transparent to the incoming visible light. It passes right through them, no problem, but they absorb the outgoing infrared radiation. They catch it. The molecules of carbon dioxide and water vapor and methane literally vibrate when they encounter infrared photons at certain wavelengths. The photon gets absorbed, the molecule gets excited, and then it re-emits the energy. But it re-emits it in a random direction. Some goes up, toward space, but some goes back down, toward the surface. The surface gets hit with energy from both above and below. Sunlight from above and back radiation from the greenhouse gases below. And that's why the surface is warmer than it would be without those gases. It's not that the heat is trapped forever. It's that the journey outward is slowed down. The greenhouse gases act like a blanket. not by stopping the heat from escaping entirely, but by making it take longer to leave, and in the process, keeping the planet warmer than it would otherwise be. Here's an analogy that might help. Imagine you're filling a bathtub and the drain is open. If water comes in from the tap and goes out the drain at the same rate, the water level stays constant. Now imagine you partially block the drain. Water is still flowing out, but more slowly. So the water level rises until the increased pressure forces water out through the partially blocked drain fast enough to match the inflow. A new equilibrium at a higher water level. That's essentially what greenhouse gases do. They partially block the outflow of energy, and the surface has to warm up until it's radiating intensely enough to push the same amount of energy out through the partially blocked drain. The energy balance restores itself, but at a higher temperature. And the beautiful thing about this explanation is that it makes a clear prediction. If you increase the concentration of greenhouse gases, if you block the drain a little more, the equilibrium temperature has to rise. More greenhouse gas, warmer planet. Less greenhouse gas, cooler planet. And that prediction, that connection between atmospheric composition and global temperature, was first made quantitatively, with actual numbers, by a Swedish scientist named Svante Arrhenius, and he did it in 1896. Which is an astonishingly long time ago when you think about it. Arrhenius is one of those figures in science who deserves to be much more famous than he is. He was born in 1859 near Uppsala, Sweden. As a child, he was a prodigy. He reportedly taught himself to read at the age of 3 by watching his father do the household accounts. He went to the University of Uppsala and then to Stockholm, and he won the Nobel Prize in Chemistry in 1903 for his work on electrolytic dissociation. Basically, his theory of how molecules break apart into ions in solution. But the thing we care about tonight is a paper he published 7 years earlier, a paper that barely anyone noticed at the time, and that turned out to be one of the most prescient scientific works of the 19th century. In 1896, Arrhenius asked a straightforward question. What would happen to the Earth's temperature if the amount of carbon dioxide in the atmosphere changed? And then he sat down and calculated it. By hand. This was 1896. No computers, no spreadsheets, no calculators. Just Arrhenius, a pencil, and months of tedious arithmetic. He used data on infrared absorption that had been collected by an American astronomer named Samuel Langley, who had measured how the moon's infrared radiation was absorbed by the Earth's atmosphere at different angles. Arrhenius took Langley's data and built a model, a very simplified one, but a model, of how changing CO2 levels would affect the radiation balance of the atmosphere. And here's what he found. He estimated that doubling the amount of carbon dioxide in the atmosphere would raise the global average temperature by about 5 to 6 degrees Celsius. Halving it would lower the temperature by a comparable amount. Now, that estimate turns out to be a bit high compared to modern calculations. The current best estimate for the warming from a doubling of CO2, what climate scientists call equilibrium climate sensitivity, is somewhere in the range of 2.5 to 4 degrees Celsius, with a central estimate around 3 degrees. But Arrhenius was in the right ballpark, which is remarkable given that he was doing this calculation in the late 19th century with extremely limited data and an incredibly simplified model. And here's the thing that's really interesting about Arrhenius. He wasn't alarmed by his finding. He actually thought it was good news. Sweden is cold. Arrhenius was living in Stockholm, and he figured that a warmer world would mean better agriculture, longer growing seasons, and a more pleasant climate, at least for northern countries. He wrote about the possibility that industrial coal burning might eventually warm the climate, and he was fairly sanguine about it. He estimated that it would take thousands of years for industrial CO2 emissions to meaningfully change the atmosphere. On that point, He was very, very wrong. But his fundamental physics, the relationship between CO2 concentration and temperature, was dead on. Now, Arrhenius was motivated by something specific, and it's worth knowing what it was, because it connects to an even bigger story. He was trying to understand ice ages. By the late 19th century, geologists had established pretty convincingly that the Earth had gone through multiple periods of extensive glaciation, ice ages, when enormous ice sheets covered much of Europe and North America. The evidence was everywhere: scratched and polished bedrock, erratic boulders deposited far from their source, distinctive landforms that could only have been carved by glaciers. The Swiss-American geologist Louis Agassiz had championed the Ice Age theory decades earlier, and by the 1890s, it was well accepted. But nobody knew what caused them. What could possibly cool the entire planet enough to bury Chicago under a mile of ice, and then warm it up again? A Scottish self-taught scientist named James Kroll had proposed in the 1860s and 1870s that variations in Earth's orbit might be responsible. The Earth's orbit isn't perfectly constant. It stretches and contracts slightly over tens of thousands of years, wobbles on its axis, changes the tilt of its poles relative to the sun. These variations change how much sunlight hits different parts of the planet at different times of year. Kroll thought these orbital changes might trigger ice ages. It was a brilliant idea, but the details didn't quite work out, and it fell out of favor. Then, in the early 20th century, a Serbian mathematician named Milutin Milankovic picked up the same thread and ran with it, much more rigorously. Milankovic spent the better part of 3 decades, including time as a prisoner of war during World War I, when he reportedly continued his calculations in his cell, working out exactly how the 3 main orbital cycles affect solar radiation at different latitudes. These are the Milankovic cycles, and they're still fundamental to our understanding of climate. Here's how they work. The first cycle is eccentricity, the shape of Earth's orbit around the Sun. It changes from nearly circular to slightly more elliptical and back over a period of about 100,000 years. When the orbit is more elliptical, the difference in solar energy received between the closest and farthest points from the Sun is larger. The second cycle is obliquity, the tilt of the Earth's axis, which is currently about 23.4 degrees. That tilt varies between about 22.1 and 24.5 degrees over a period of about 41,000 years. A bigger tilt means more extreme seasons, hotter summers, colder winters. The third cycle is precession, the slow wobble of the Earth's axis, like a spinning top that's winding down. This cycle takes about 26,000 years and changes which hemisphere is tilted toward the Sun at the point of closest approach. None of these cycles change the total amount of sunlight hitting the Earth very much. That's important. They mainly change the distribution, when and where the sunlight arrives. And Milankovic figured out that the critical factor wasn't how cold the winters were, it was how cool the summers were in the northern hemisphere, around 65 degrees north latitude, because that's where the big land masses are: northern Canada, Scandinavia, Siberia. If summers at those latitudes are cool enough that the winter snow doesn't completely melt, it accumulates. Year after year, decade after decade, the snow builds up, compresses into ice, and you start to grow an ice sheet. And once you have a big white ice sheet, it reflects more sunlight back into space, which cools things further, which helps the ice grow more. It's a feedback loop. We'll talk a lot about those tonight, and it can amplify a relatively small orbital nudge into a full-blown ice age. Now, here's where Arrhenius connects to all of this. He realized that orbital cycles alone might not be enough to explain the full magnitude of the ice ages. The orbital changes in solar energy are pretty small, maybe a few percent at most. You'd need something to amplify them, and he proposed that CO2 might be that amplifier. As the planet cooled, CO2 levels might drop, perhaps because cooler oceans absorb more CO2, or because chemical weathering slows down, and lower CO2 would mean less greenhouse warming, which would cool the planet further. And the reverse, on the way out of an ice age, warming oceans would release CO2, boosting the greenhouse effect, amplifying the warming. CO2 as both a cause and a consequence. A feedback loop, again. And it turns out, he was essentially right about that too. We now have incredibly detailed records from ice cores, drilled from the Antarctic ice sheet, that show the intimate relationship between CO2 and temperature over the past 800,000 years. But that's getting ahead of the story. We'll come back to ice cores later, because they're one of the most beautiful and important datasets in all of science. And there's a side note here that's worth mentioning, because it connects to something we'll talk about later. Arrhenius was also friends with a fellow Swedish scientist named Arvid Högbohm, who had been studying the carbon cycle from a geological perspective, looking at how much CO2 volcanoes emit, how much gets absorbed by weathering, the whole planetary budget. And Högbohm had estimated, even back in the 1890s, that human industrial emissions of CO2 were roughly comparable to the amount released by volcanoes each year. That's a striking observation. It meant that humanity was already, by the late 19th century, operating as a geological force, moving carbon on a scale that rivaled the Earth's own internal processes. And Arrhenius knew this. He just didn't think it was going to be a problem anytime soon. As it turned out, the scale of fossil fuel burning was about to increase dramatically. Through 2 world wars, through the post-war industrial boom, through the explosive growth of the automobile and the electrification of the developing world, and the timeline Arrhenius imagined would prove wildly optimistic. After Arrhenius, the study of CO2 and climate went quiet for a while. Decades, actually. And there are a few reasons for that. One is that many scientists at the time believed the oceans would simply absorb any excess CO2 that humans produced. The oceans are enormous. They contain something like 50 times more carbon than the atmosphere, so it seemed reasonable to assume they'd just soak up whatever we emitted, keeping atmospheric levels stable. Another reason is that early spectroscopic measurements seemed to show that the CO2 absorption bands were already saturated, meaning the CO2 already in the atmosphere was absorbing all the infrared radiation it could at those wavelengths, so adding more wouldn't make a difference. This was the saturation argument, and it was used for decades to dismiss the idea that increasing CO2 could warm the climate. It seemed like a strong argument, and it was wrong, for subtle but important reasons that we'll get to. The person who pulled the question of CO2 and climate back from obscurity was, improbably, a British steam engineer and amateur meteorologist named Guy Stewart Callendar. Callendar wasn't an academic. He was a steam and fuel technologist, the son of a physicist, and he studied climate in his spare time because it fascinated him. In 1938, he presented a paper to the Royal Meteorological Society in London, arguing that the burning of fossil fuels was measurably increasing the CO2 content of the atmosphere, and that this increase was already warming the climate. He had compiled temperature records from around the world and found a warming trend over the previous half-century. He had gathered CO2 measurements from various sources and shown that levels were rising, and he connected the two, arguing that the warming was at least partly caused by the CO2 increase. The reception was polite but skeptical. Several senior scientists at the meeting pushed back. The same objections came up. The oceans would absorb the CO2, the absorption bands were saturated, the temperature record was too short and too unreliable. Callendar pushed back himself, arguing carefully from the data, but the establishment wasn't convinced. He continued publishing on the subject for years. The connection between CO2 and warming is sometimes called the calendar effect, but he remained a somewhat marginal figure in his own time, an amateur telling the professionals something they didn't want to hear. But here's the thing about calendar. He was right. Not about every detail. His estimates of the warming rate were imprecise, his temperature data was incomplete, and his understanding of the carbon cycle was simplified. But on the fundamental point, that human CO2 emissions were accumulating in the atmosphere and would warm the climate, he was absolutely, prophetically correct. And it took mainstream science another 20 years to catch up with him. The reason it took that long is partly because the saturation argument seems so convincing. So let me take a minute to explain why it's wrong. Because this comes up even today, and it's worth understanding. The argument goes like this. If you look at the infrared absorption spectrum of CO2, there's a strong absorption band centered around a wavelength of 15 micrometers. At current CO2 levels, the atmosphere already absorbs essentially all the outgoing infrared radiation at that specific wavelength within the first few meters above the surface. So the center of the absorption band is indeed saturated. Adding more CO2 doesn't make a difference at that exact wavelength. Case closed, right? Wrong. And here's why. The absorption band isn't infinitely narrow. It has wings, frequencies near the center where absorption is weaker, but not zero. As you add more CO2, those wings get wider. More and more frequencies get absorbed. The band effectively broadens. More importantly, and this is the subtler part, the saturation argument misunderstands how the greenhouse effect actually works in a thick atmosphere. It's not about absorbing radiation near the surface. It's about where the atmosphere becomes transparent enough that radiation can finally escape to space. Think of it this way. The atmosphere radiates energy to space, primarily from its upper layers, where the air is thin enough that infrared photons can escape without being reabsorbed by another greenhouse gas molecule. This altitude is sometimes called the effective emission height. If you add more CO2, that emission height moves upward, because the atmosphere has to be thinner before it becomes transparent enough. And the higher you go in the troposphere, the colder it is. A colder emitting layer means less energy radiated to space. Less energy out, same energy in from the sun. The planet has to warm up until the outgoing radiation rises enough to restore balance. It's a subtle argument, and it took some very clever physicists to work it out properly. But the short version is, no, the greenhouse effect is not saturated. Adding more CO2 does trap more heat. The physics is clear, and it's been confirmed by laboratory measurements, by satellite observations of outgoing radiation, and by basic radiative transfer calculations that have been checked and rechecked since the 1950s. And it was in the 1950s that the pieces really started coming together, because two scientists, working at the same institution actually, in La Jolla, California, launched what would become the most important measurement program in the history of climate science. Their names were Roger Revelle and Charles David Keeling, and the story of how they started measuring CO2 from the top of a Hawaiian volcano is one of those stories that changed the world, even though almost nobody noticed at the time. Roger Revelle was an oceanographer, a big personality, a man who ran the Scripps Institution of Oceanography, and had a talent for asking the right questions. In the mid-1950s, Revelle and a colleague named Hans Suess published a paper that demolished one of the key objections to the CO2 warming theory, the idea that the oceans would simply absorb all the extra CO2. Revelle and Suess showed that ocean chemistry is more complicated than that. There's a chemical buffering system in seawater involving dissolved CO2, carbonic acid, bicarbonate, and carbonate ions. And this buffering system means that the ocean's capacity to absorb additional CO2 from the atmosphere is much more limited than people had assumed. The ocean does absorb a lot of CO2, but not all of it, and not quickly. Ravel wrote a famous line in that paper, calling the situation a large-scale geophysical experiment. Humanity was changing the composition of the atmosphere, and he wrote that neither the magnitude nor the consequences of this experiment were fully understood. That was 1957. And then Ravel did something crucial. He helped arrange funding for a young postdoctoral researcher named Charles David Keeling to set up instruments to measure atmospheric CO2 with unprecedented precision. Keeling was, in many ways, the perfect person for this job. He was meticulous to the point of obsession. He cared about measurement accuracy the way some people care about music or food. It wasn't just a professional requirement, it was a personal passion. He'd built his own instruments, calibrated them with extraordinary care, and he insisted on measuring CO2 with a precision of better than 1 part per million. This might not sound like a big deal, but at the time it was groundbreaking. Previous CO2 measurements had been scattered, inconsistent, taken at various locations with various instruments, and varying degrees of rigor. The data was noisy. You couldn't see a clear trend in it. Keeling wanted to change that. He set up his primary monitoring station on the summit of Mauna Loa, a volcano on the Big Island of Hawaii, and the choice of location was deliberate and clever. Mauna Loa sits in the middle of the Pacific Ocean, far from any major industrial sources or large forests or other local influences that might skew the readings. At 3,400 meters above sea level, the instruments are well above the boundary layer, that lowest part of the atmosphere where local conditions cause a lot of variability, and the air that reaches Mauna Loa has typically been mixed across thousands of kilometers of open ocean. It's about as representative of the global background atmosphere as you can get, and there's a lovely detail about Keeling that I think captures the kind of person he was. Before setting up the Mauna Loa station, he spent time taking CO2 measurements in the mountains of California, at Big Sur on the coast, and in various other locations, painstakingly calibrating his instruments, comparing his results against primary standards he'd developed himself. He discovered something subtle and beautiful. At remote locations, if you measured CO2 in the early afternoon, when vertical air mixing was strongest, the readings converged on a consistent value, not the same everywhere in the world, but consistent at each location, with a diurnal pattern that reflected the local biosphere breathing in and out. That consistency told him that there really was a global background level of CO2, and that it could be measured precisely if you were careful enough. He was right, and that precision, that insistence on getting the measurement right, not approximately right, but actually right, is what made the Keeling curve possible. Keeling started taking measurements in March 1958, and almost immediately he noticed something. The CO2 level was rising. Not chaotically, not unpredictably, but in a smooth, unmistakable upward curve. There was a seasonal oscillation. CO2 dropped in the northern hemisphere summer, when plants are absorbing it through photosynthesis, and rose in winter, when the plants shed their leaves and decomposition releases carbon. This seasonal breathing, the Earth literally inhaling and exhaling CO2 over the course of each year, was beautiful. It was the biosphere, visible in the data, but overlaid on top of that seasonal cycle was an unmistakable upward trend. Year after year, the baseline was rising. When Keeling started measuring in 1958, the CO2 concentration was about 315 parts per million. By the time he died in 2005, it had reached about 380 parts per million, and as of the mid-2020s, it's over 420 parts per million. That's a roughly 33% increase since the late 1950s, and about a 50% increase over pre-industrial levels, which were around 280 parts per million. The graph of this rise, CO2 concentration on the y-axis, year on the x-axis, is called the Keeling curve, and it is one of the most important scientific graphs ever created. It's been called the most important geophysical record of the 20th century. And the curve doesn't level off. It doesn't plateau. It rises year after year, decade after decade, with that gentle, seasonal oscillation rippling on top of the relentless upward climb. Now let me take a step back and talk about where all this carbon dioxide is actually coming from, because the carbon cycle is one of those things that sounds simple on the surface, but is actually a fascinating, intricate, beautiful system. Carbon is one of the most important elements in the universe, at least as far as life is concerned. Every organic molecule, every protein, every strand of DNA, every fat, every carbohydrate, they're all built on a backbone of carbon atoms. And on Earth, carbon is constantly moving between different reservoirs: the atmosphere, the oceans, the rocks, the soil, the biosphere, in a grand cycle that has been running for billions of years. Here's the basic picture. Carbon dioxide in the atmosphere gets absorbed by plants through photosynthesis. The plants use the carbon to build their tissues: trunks, leaves, roots. Animals eat the plants and incorporate the carbon into their own bodies. When plants and animals die and decompose, or when they're eaten by other organisms, some of the carbon goes back into the atmosphere as CO2 through respiration and decay. Some of it gets buried in sediments, and over millions of years, that buried organic carbon can be transformed by heat and pressure into coal, oil, and natural gas, fossil fuels. Some carbon dissolves in the oceans, where it participates in a whole parallel set of chemical reactions, and some of it ends up in the shells and skeletons of marine organisms like corals and foraminifera, made of calcium carbonate. When those organisms die and their shells sink to the ocean floor, they eventually get compressed into limestone, locking the carbon into rock for millions of years. And there are processes going in the other direction too. Volcanoes release CO2 from deep within the earth, returning carbon from the geological reservoir to the atmosphere. On average, volcanoes emit somewhere around 200 to 300 million tons of CO2 per year, which sounds like a lot until you compare it to human emissions, which are more than 100 times larger. Chemical weathering of rocks, where rainwater, which is naturally slightly acidic because it absorbs CO2 from the air and forms carbonic acid, slowly dissolves minerals in exposed rock. That process pulls CO2 out of the atmosphere over long timescales. It's nature's own carbon capture system, but it operates over millions of years, far too slowly to offset what we're doing now. The whole thing is a cycle, an enormous, slow, interconnected cycle, and for most of Earth's history, it's been roughly in balance. Carbon flows in, carbon flows out. The atmospheric concentration drifts up and down over millions of years, driven by volcanic activity and weathering rates, and changes in how much life there is and how it's distributed. There have been times when CO2 was much higher than today. In the age of the dinosaurs, atmospheric CO2 may have been 4 to 8 times current levels, and the planet was much warmer, with no polar ice caps. There have been times when it was lower, during the great ice ages of the past few million years. But on the timescales that matter for civilization, centuries and millennia, the system was pretty stable. The carbon cycle had reached a kind of equilibrium, a dynamic balance where the inputs and outputs roughly matched. Until we started digging up those fossil fuels and burning them. Think about what fossil fuels actually are. They're concentrated stores of ancient sunlight. Hundreds of millions of years ago, plants and tiny marine organisms absorbed carbon dioxide from the atmosphere, used the sun's energy to build carbon-based molecules, And then, when they died, some of their remains got buried under layers of sediment before they could decompose. Over geological time, heat and pressure transformed those carbon-rich deposits into coal, oil, and natural gas. That carbon was effectively removed from the active carbon cycle. It was locked away, underground, out of the game. And it would have stayed there for millions more years, gradually recycled by geological processes, if we hadn't come along and found a use for it. When we burn a lump of coal or a gallon of gasoline, we're taking carbon that was sequestered underground for hundreds of millions of years and releasing it back into the atmosphere in seconds. We're taking geological timescales and compressing them into human timescales. We're short-circuiting the carbon cycle, and the numbers are staggering. Humanity currently emits something on the order of 36 to 37 billion metric tons of CO2 per year from fossil fuel combustion and industrial processes. Billion, with a B. Add in land use changes like deforestation, cutting down forests that were storing carbon and either burning them or letting them decay, and the total goes even higher, to around 40 billion tons or more per year. Now, the natural carbon cycle does absorb a significant portion of those emissions. The oceans are currently absorbing about 25 to 30% of the CO2 we emit. Terrestrial ecosystems, forests, soils, grasslands, absorb another 25 to 30%. But that still leaves about 40 to 45% of our emissions accumulating in the atmosphere each year, year after year, pushing the Keeling curve inexorably upward. And this is where those ice cores I mentioned earlier come back into the story, because they give us something extraordinary, a window into the past, a very, very deep window. When snow falls on a place like Antarctica or Greenland and doesn't melt, it gradually gets compressed under the weight of more snow on top of it, and over time it turns into ice. And as it does, tiny bubbles of air get trapped inside the ice. Those air bubbles are actual samples of the ancient atmosphere, preserved for millennia. By drilling deep into the ice sheet and pulling up long cylinders of ice cores, scientists can extract those air bubbles and measure the CO2 concentration of the atmosphere at the time the ice formed. They can date the ice layers by counting annual layers, by measuring the chemical composition, by correlating with volcanic eruptions that left distinct traces. And the deeper you drill, the further back in time you go. The most famous ice core records come from Antarctica, from a Soviet and then Russian drilling station called Vostok, and from the European project for ice coring in Antarctica, EPICA, at a location called Dome C. The Vostok core, drilled over several decades starting in the 1970s, eventually reached a depth of over 3,600 meters and went back about 420,000 years. The EPICA core, completed in 2004, goes back about 800,000 years. 800,000 years. Think about that. That core contains a continuous record of atmospheric composition and temperature stretching back through 8 complete glacial cycles, 8 ice ages, and the warm periods in between. And the process of getting these cores is itself a remarkable story of engineering and endurance. Vostok Station, where the Russian core was drilled, is one of the coldest places on Earth. The average annual temperature there is minus 55 degrees Celsius. The lowest temperature ever reliably recorded on Earth's surface, minus 89.2 degrees Celsius, in July 1983, was measured at Vostok. Scientists lived and worked there for months at a time, operating drilling equipment in conditions that would be considered extreme on Mars. The drill itself had to be specially designed to operate at such low temperatures, using an antifreeze fluid in the borehole to prevent it from closing under the pressure of the surrounding ice. The ice cores were brought up in segments, each about a meter long, carefully labeled, stored in cold rooms, and eventually shipped to laboratories around the world for analysis. Each segment represents a few decades or centuries of snowfall, compressed and preserved. A time capsule of ancient air. The analysis is painstaking. Scientists cut thin slices of the ice, melt them in sealed containers, and measure the gas composition of the released bubbles using mass spectrometers. They can determine not only the CO2 concentration, but also methane levels, nitrous oxide levels, and even the isotopic composition of the water molecules in the ice itself, which serves as a proxy for temperature. Heavier isotopes of oxygen and hydrogen evaporate less readily, so the ratio of heavy to light isotopes in the ice depends on how cold it was when the snow fell. It's an indirect measurement, a proxy, but it's been extensively validated against other temperature indicators, and it gives a remarkably reliable record. And when you look at that record, two things jump out immediately. First, temperature and CO2 track each other with remarkable fidelity. When CO2 goes up, temperature goes up. When CO2 goes down, temperature goes down. They dance together through 8 glacial cycles, rising and falling in concert. The correlation is stunning, one of the tightest relationships in all of climate science. And here's where another pivotal figure enters the story. A man named Wallace Broecker, usually known as Wally Broecker, a geochemist at Columbia University's Lamont Doherty Earth Observatory. Broecker was a big, forceful personality, the kind of scientist who would say exactly what he thought, loudly, and make you deal with it. He was one of the first to use the phrase global warming in a scientific paper, back in 1975. His paper was titled, "Climatic Change: Are We on the Brink of a Pronounced Global Warming?" And yes, that was 1975, 50 years ago, and the answer to his question turned out to be yes. But Broecker's most important contribution was his work on abrupt climate change. He studied the ice core records and the sediment records from the ocean floor, and he found something deeply unsettling. Climate doesn't always change gradually. Sometimes it lurches. Sometimes it flips. The most dramatic example is a period called the Younger Dryas, about 12,800 years ago. The planet was warming up. Coming out of the last ice age, glaciers were retreating. Things were heading in a pleasant direction. And then, in maybe a decade or two, a geological instant, temperatures in the North Atlantic region plummeted by something like 5 to 10 degrees Celsius and stayed cold for more than 1,000 years before snapping back to warm conditions almost as abruptly. 1,000 years of ice age conditions inserted right in the middle of a warming trend, starting and ending in the span of a human lifetime. Broecker argued that this was caused by a disruption of the Atlantic Ocean's circulation, the same system of deep currents that we now call the Atlantic Meridional Overturning Circulation, the AMOC. Fresh water from melting glaciers, he proposed, flooded into the North Atlantic and disrupted the density-driven sinking of cold, salty water that powers the whole circulation. The heat conveyor belt shut down. Europe froze. And when conditions shifted again, it snapped back on, and the warming resumed. The lesson from the Younger Dryas, and from Broecker's work more broadly, is that the climate system has thresholds. It's not like a thermostat that adjusts smoothly. It's more like a light switch that can flip suddenly from one state to another. And once it flips, it may not flip back easily. Broecker famously compared the climate system to an angry beast that we were poking with a stick. He said we'd be foolish to assume the response would be gentle and proportional. Sometimes the beast wakes up. Now, as I mentioned earlier when we talked about Milankovitch cycles, the initial trigger for these glacial cycles is orbital, changes in how sunlight is distributed across the Earth's surface. The CO2 changes are partly a response to the temperature changes, not only a cause of them. Warming oceans release CO2. Cooling oceans absorb it. But the CO2 then acts as a powerful amplifier, reinforcing and extending the warming or cooling that the orbital nudge started. It's both cause and effect, part of a feedback loop, and this is one of the things that sometimes confuses people, but is actually crucial to understand. The fact that CO2 changes sometimes lag behind temperature changes in the ice core record doesn't mean CO2 doesn't drive warming. It means the relationship is more subtle than simple cause and effect. Both are true. CO2 responds to temperature, and temperature responds to CO2. The second thing that jumps out of the ice core record is the range of natural variation. Over the past 800,000 years, CO2 levels have oscillated between about 180 parts per million during the depths of ice ages and about 280 parts per million during the warm interglacial periods. That's the natural range, 180 to 280. The rhythm is remarkably regular. And then you look at where we are now, over 420 parts per million and rising fast. We have blown past the upper end of the natural range by a margin that has no precedent in at least 800,000 years. Probably much longer than that. There's geological evidence suggesting that CO2 levels haven't been this high in several million years, perhaps not since the Pliocene epoch, when sea levels were significantly higher than today, and the planet was considerably warmer. Now let's come back to the mid-20th century, because the scientific understanding of climate was about to take a huge leap forward, and it was going to do it in an unlikely place, inside a computer. Well, inside the very earliest computers, which were the size of rooms and less powerful than the phone in your pocket. The person who did more than anyone else to bring computers and climate together was a quiet, intensely focused Japanese-American meteorologist named Syukuro Manabe. Manabe was born in 1931 in Ehime Prefecture on the island of Shikoku, Japan. He studied meteorology at the University of Tokyo and came to the United States in 1958 to work at the U.S. Weather Bureau, which later became part of NOAA. He ended up spending most of his career at the Geophysical Fluid Dynamics Laboratory in Princeton, New Jersey, and in 2021, at the age of 90, he shared the Nobel Prize in Physics for his work on climate modeling. When he was interviewed about winning the Nobel, he was characteristically modest and slightly bemused, saying he had never imagined his work on climate simulations would be considered physics. But it was. It absolutely was. Here's what Manabe did. In the mid-1960s, working with a colleague named Richard Weatherald, he built one of the first rigorous computer models of the atmosphere's vertical temperature structure, what scientists call a radiative convective model. This was a one-dimensional model. It represented the atmosphere as a single column of air, divided into layers, and calculated how energy moved up and down through those layers via radiation and convection. It was simplified compared to the real three-dimensional atmosphere, but it captured the essential physics. And in 1967, Manabe and Weatherald published a landmark paper showing the results. When they doubled the CO2 in their model, the surface temperature rose by about 2.3 degrees Celsius. This was the first truly rigorous computational estimate of climate sensitivity, and it remains remarkably close to modern estimates. That paper is one of the most cited in the history of climate science, but Manabe didn't stop there. He went on to build three-dimensional climate models, general circulation models, or GCMs, that simulated the whole atmosphere, including wind patterns, moisture transport, and eventually the oceans. These models divided the Earth's surface into a grid of cells, each one typically a few hundred kilometers on a side, and calculated the physics in each cell at each time step. Temperature, pressure, humidity, wind speed, cloud formation, all governed by the fundamental equations of fluid dynamics and thermodynamics. It was an enormous computational challenge, even for the best computers available. Each model run took hours or days, and the resolution was crude by modern standards. But the models worked. They produced recognizable weather patterns. They captured the jet streams, the trade winds, the monsoons. And when you increased the CO2, they warmed up, just as the simpler models predicted. Now, you might be wondering, why should we trust a computer model? It's a fair question. And the answer is that climate models aren't trusted because someone says so. They're tested rigorously. You can run a climate model with the known conditions of the past, the solar output, the volcanic eruptions, the CO2 levels, and see if it reproduces the climate that actually occurred. This is called hindcasting, and modern climate models do it remarkably well. They reproduce the observed temperature trends of the 20th century. They capture the cooling effect of major volcanic eruptions like Pinatubo in 1991. They reproduce the broad patterns of ice ages when driven with Milankovitch orbital parameters and observed CO2 levels. None of this proves the models will be perfectly right about the future, of course, but it gives you a good reason to take their projections seriously. They embody real physics, they're tested against real observations, and they've been getting better for 60 years. And before we get to the pivotal moment when climate change hit the public stage, let me take a quick detour to tell you about something that actually went right, spectacularly right, in the history of atmospheric science, because it's relevant and it's encouraging. The ozone layer. High up in the stratosphere, roughly 15 to 35 kilometers above the surface, there's a thin layer of ozone, O3, 3 atoms of oxygen bonded together instead of the usual 2. This layer absorbs most of the sun's ultraviolet radiation, particularly the high-energy UVB and UVC that would otherwise reach the surface and cause skin cancer, cataracts, and damage to plant life and marine ecosystems. The ozone layer is, in a very real sense, the sunscreen of the planet, and in the 1970s and 1980s, scientists discovered that it was being destroyed. In 1974, 2 chemists, Mario Molina and Sherwood Rowland at the University of California, Irvine, published a paper showing that chlorofluorocarbons, CFCs, these incredibly useful industrial chemicals used as refrigerants, aerosol propellants, and solvents, were drifting up into the stratosphere and being broken apart by ultraviolet light. The chlorine atoms released in the process were catalytically destroying ozone molecules. Each chlorine atom could destroy thousands of ozone molecules before being deactivated. Molina and Rowland were sounding an alarm, and the world, slowly, listened. The confirmation came dramatically. In 1985, a team of British scientists, led by Joe Farman, working at the Halley Research Station in Antarctica, published measurements showing a massive, unexpected decline in ozone levels over the Antarctic each spring, the ozone hole. NASA had actually been measuring ozone from satellites, but their computers had been programmed to flag anomalously low readings as errors, so the data had been filtered out. When they went back and reprocessed it, the hole was clearly visible. This was a wake-up call. What happened next is one of the great success stories of international environmental cooperation. In 1987, nations around the world signed the Montreal Protocol, agreeing to phase out the production and use of CFCs and other ozone-depleting substances. The protocol has been ratified by every country on Earth, 198 parties, universal membership, the only international treaty to achieve that, and it worked. CFC concentrations in the atmosphere have been declining steadily, and the ozone layer is slowly recovering. Current projections suggest the ozone hole will be fully healed by the middle of this century, though it's a slow process, because CFCs are long-lived in the atmosphere. Now, the ozone problem was in some ways easier than the climate problem. The chemicals involved were made by a small number of companies. Substitutes were available, The economic disruption was manageable. Climate change involves the global energy system. Coal, oil, and gas are the bedrock of the world economy, and transitioning away from them is immensely more complex. But the Montreal Protocol proved something important. When the science is clear, when the risks are understood, and when the political will exists, humanity can act collectively to protect the atmosphere. It can be done. And then there's the track record of specific predictions. This brings us to one of the most pivotal moments in the public history of climate science. June 23, 1988. A brutally hot day in Washington, D.C. Temperature of 101 degrees Fahrenheit. Air conditioning in the hearing room, allegedly turned off, some said deliberately, to make the heat more visceral. And a NASA climate scientist named James Hansen sat before a U.S. Senate committee and said something that no scientist of his stature had said so publicly before. The greenhouse effect had been detected, and it was changing our climate. Hansen had been working on climate models at NASA's Goddard Institute for Space Studies in New York since the late 1960s. He was, and is, an intensely serious person. A former student of James Van Allen, the space physicist who discovered Earth's radiation belts. Hansen grew up on a farm in Iowa, studied under Van Allen at the University of Iowa, and initially worked on modeling the atmospheres of Venus and other planets, before turning his attention to Earth's climate. There's something fitting about that trajectory. He understood the greenhouse effect on Venus before he understood it on Earth. He knew what an atmosphere could do when things went wrong. And by the late 1980s, his models were telling him that things were starting to go wrong on this planet too. Hansen had spent years refining his climate models and studying the temperature record, and by 1988, he was confident enough to make his statement. He told the senators that the warming trend was not natural variability, that he was 99% certain the warming was caused by the buildup of greenhouse gases. That was a remarkably strong statement for a working scientist to make in a public hearing. Many of his colleagues thought he was getting ahead of the evidence, being too bold, too certain. But Hansen believed the risks of understating the problem were greater than the risks of overstating it. He was willing to take the heat, so to speak. He presented 3 scenarios for future warming, based on different assumptions about future greenhouse gas emissions. Scenario A assumed emissions would continue accelerating. Scenario B assumed emissions would grow more slowly and then level off. Scenario C assumed drastic cuts in emissions starting in the year 2000. 30-plus years later, we can check how his predictions held up. The actual emissions trajectory has roughly followed Scenario B, and the observed warming has tracked remarkably close to his Scenario B projection. Not perfectly. No model prediction ever is. But close. Hansen's 1988 projections got the big picture right. The world has warmed roughly in line with what his models predicted, given the emissions that actually occurred. That's not luck. That's physics. Hansen's testimony was a watershed moment. It put climate change on the front page. It made it a political issue, and it ultimately led, just a few months later, to the creation of the Intergovernmental Panel on Climate Change, the IPCC, established by the United Nations Environment Program and the World Meteorological Organization in 1988. The IPCC doesn't do new research. What it does is synthesize the existing research. Every few years, it gathers thousands of scientists from around the world to review the published scientific literature on climate change and produce a comprehensive assessment report. The first assessment came out in 1990. The most recent, the 6th assessment report, was completed in 2023, and with each successive report, the language has grown more confident, more definitive, more stark. The first assessment report in 1990 said that global mean surface temperature had increased by 0.3 to 0.6 degrees Celsius over the last 100 years, and that this was broadly consistent with predictions of greenhouse gas-driven warming, but that the observed magnitude was also within the range of natural variability. In other words, it could be greenhouse warming, but we can't be sure yet. The second assessment report in 1995 took a step further, with its famous, carefully worded statement, "The balance of evidence suggests a discernible human influence on global climate." By the fourth assessment report in 2007, the language was much stronger. Warming of the climate system was unequivocal, and most of the observed increase in globally average temperatures since the mid-20th century was very likely due to the observed increase in anthropogenic greenhouse gas concentrations. Very likely, in IPCC language, means more than 90% probability, and the sixth assessment report in 2021 removed virtually all remaining hedging. It is unequivocal that human influence has warmed the atmosphere, ocean, and land. So, how do we actually know it's us? This is worth spending a minute on, because there are multiple independent lines of evidence, and each one tells the same story. First, there's the isotopic signature. Carbon comes in different isotopes, carbon-12, carbon-13, and carbon-14, and fossil fuels have a distinctive isotopic fingerprint. Plants prefer the lighter isotope, carbon-12, during photosynthesis, so the carbon in fossil fuels is depleted in carbon-13 relative to carbon in the atmosphere. As we burn fossil fuels and add their carbon to the atmosphere, the ratio of carbon-13 to carbon-12 in atmospheric CO2 has been declining. That's exactly what you'd expect if the extra CO2 is coming from burned ancient plant material. Similarly, carbon-14 is radioactive with a half-life of about 5,700 years, so fossil fuels, which are millions of years old, contain essentially no carbon-14 at all. The proportion of carbon-14 in atmospheric CO2 has been decreasing, again, consistent with a fossil fuel source. Second, there's the oxygen correlation. When you burn a fossil fuel, say coal, which is mostly carbon, each carbon atom combines with 2 oxygen atoms to form CO2. So you'd expect atmospheric oxygen levels to decline slightly as CO2 levels rise, because burning consumes oxygen. And indeed, precise measurements show that atmospheric oxygen has been declining at almost exactly the rate you'd predict from fossil fuel combustion. Third, the spatial pattern of warming matches what greenhouse gas models predict. The warming is greater at night than during the day, greater in winter than in summer at high latitudes, greater at the surface than in the upper atmosphere. In fact, the stratosphere, the layer of the atmosphere above the troposphere, is actually cooling, which is a very specific prediction of greenhouse warming and is very hard to explain by any other mechanism. If the warming were caused by increased solar output, for example, you'd expect the stratosphere to warm too. It's cooling. That's the greenhouse gas fingerprint. Fourth, there's the sheer magnitude and speed of the change. Natural climate forcings, solar variations, volcanic eruptions, orbital changes, are either too small, too slow, or going in the wrong direction to explain the observed warming. Solar output has been flat or slightly declining since the 1980s, while temperatures have continued to rise. The orbital changes that drive ice ages operate on timescales of tens of thousands of years, not decades. No natural factor, or combination of natural factors, can reproduce the observed warming pattern without including greenhouse gas increases. When you run climate models with only natural forcings, they don't warm. When you add the human-caused greenhouse gas increases, they match the observations. It's a very clean result. Now, let's talk about feedback loops, because this is where the climate system goes from being complicated to being genuinely complex, and it's where a lot of the uncertainty in climate projections comes from. The basic greenhouse effect, the direct warming from adding CO2, is actually fairly well understood and not hugely controversial. If you double CO2 and nothing else changed, the planet would warm by about 1.1 to 1.2 degrees Celsius. That's the number you get from straightforward physics, from basic radiative transfer calculations. But of course, nothing else stays the same. Warming the planet triggers a cascade of changes, and those changes can either amplify the original warming, positive feedbacks, or dampen it, negative feedbacks. And the net effect of all these feedbacks is what determines the total warming you actually get. The most important positive feedback is water vapor. This one is powerful and well understood. As the planet warms, more water evaporates from the oceans, rivers, and soil. Water vapor is itself a greenhouse gas. In fact, it's the most important greenhouse gas in terms of its total contribution to the natural greenhouse effect. So more warming means more water vapor, which means more greenhouse warming, which means more evaporation, which means more water vapor. It's a self-reinforcing cycle. This single feedback roughly doubles the warming you'd get from CO2 alone. Without the water vapor feedback, climate sensitivity would be about half of what it actually is. Now you might think, wait, if water vapor amplifies warming, couldn't it run away entirely? Could we get a runaway greenhouse effect? And the answer is, not on Earth, not with the amount of CO2 we're adding, but it's a legitimate question, and it connects to something genuinely fascinating about our planetary neighbors. Venus, which is roughly the same size as Earth and at a similar distance from the Sun, did experience a runaway greenhouse effect at some point in its past. Venus's atmosphere is about 96% CO2, with surface pressures 90 times Earth's and surface temperatures of about 460 degrees Celsius, hot enough to melt lead. Venus is the greenhouse effect taken to its logical extreme. Earth is in no danger of becoming Venus. We'd need to add far more CO2 than exists in all the world's fossil fuel reserves. But the comparison is instructive. It shows that the greenhouse effect is real. It's powerful, and under extreme enough conditions, it can transform a planet. The second major feedback is ice albedo feedback. Albedo is just a fancy word for reflectivity. Ice and snow are white. They reflect a lot of incoming sunlight back into space. As the planet warms and ice melts, sea ice in the Arctic, glaciers on mountains, the edges of the great ice sheets, that bright, reflective surface is replaced by darker ocean water or darker land, which absorbs more sunlight. More absorption means more warming, which means more ice melts, which means more absorption, another self-reinforcing cycle. This feedback is especially strong in the Arctic, which is why the Arctic is warming roughly 2 to 4 times faster than the global average. The sea ice is shrinking, the albedo is dropping, and the warming is accelerating. Then there are cloud feedbacks, and this is where things get genuinely tricky. Clouds are complicated. They can both warm and cool the planet, depending on the type and altitude. High, thin cirrus clouds tend to warm. They're relatively transparent to sunlight, but absorb outgoing infrared radiation, acting like a greenhouse blanket. Low, thick cumulus and stratus clouds tend to cool. They reflect a lot of incoming sunlight back to space, acting like a parasol. The net effect of clouds in the current climate is slightly cooling. They reflect more sunlight than they trap in heat. But what happens to clouds as the planet warms? Do you get more high clouds or more low clouds? Do clouds get thicker or thinner? Do cloud tops rise, which would increase their warming effect? Do marine stratocumulus decks, which cool the oceans over vast areas of the subtropical Pacific, thin out or break up as CO2 levels rise? That last question, about stratocumulus breakup, was the subject of a paper published in 2019 by a researcher named Tapio Schneider and his colleagues at Caltech. Using high-resolution cloud simulations, they found that at very high CO2 concentrations, roughly 1,200 parts per million, about 3 times current levels, stratocumulus clouds could abruptly dissipate, exposing the ocean surface to much more sunlight and causing a rapid further warming of about 8 degrees Celsius on top of whatever warming had already occurred. Now, reaching 1,200 parts per million would require burning through far more fossil fuel than most scenarios project, so this is unlikely in the near term. But it illustrates how cloud feedbacks can harbor nasty surprises, and it underscores why getting cloud physics right is so important for climate projections. These questions are among the hardest in climate science, and they're a major source of the remaining uncertainty in climate sensitivity estimates. Different models handle clouds differently, and that's a big reason why the range of climate sensitivity, 2.5 to 4 degrees for a doubling of CO2, is still relatively wide. And then there are the really scary feedbacks, the ones that might kick in at higher levels of warming and that are harder to predict. Permafrost feedback is a big one. Permafrost is permanently frozen ground, found across vast areas of Siberia, Alaska, Canada, and the Tibetan Plateau. It contains enormous amounts of organic matter, dead plants and animals frozen in the soil for thousands, or even tens of thousands of years. As the Arctic warms and the permafrost thaws, that organic matter starts to decompose, and decomposition releases CO2 and methane. Methane is a particularly potent greenhouse gas. Molecule for molecule, it traps about 80 times more heat than CO2 over a 20-year period, though it breaks down faster. The amount of carbon locked up in permafrost is estimated to be roughly twice the amount currently in the atmosphere. If even a fraction of that is released as the Arctic warms, it would significantly amplify warming, and the process would be very difficult to stop. You can reduce human emissions, but you can't refreeze the permafrost once it's thawing. This brings us to the concept of tipping points, and this is genuinely important. A tipping point is a threshold beyond which a change becomes self-reinforcing and irreversible, at least on human timescales. Think of a ball sitting in a shallow bowl. You can push it a little and it rolls back. But if you push it hard enough, it rolls over the rim and falls off the table. It's not going to roll back up on its own. Climate scientists have identified several potential tipping points in the Earth system. The collapse of the West Antarctic ice sheet, which holds enough ice to raise sea levels by about 3 to 5 meters. The dieback of the Amazon rainforest, which could turn from a carbon sink into a carbon source. The shutdown of the Atlantic meridional overturning circulation, the ocean current system that includes the Gulf Stream and transports heat from the tropics to northern Europe. The loss of Arctic summer sea ice, the thawing of permafrost. The worry isn't just that any one of these might be triggered. It's that they could cascade, one tipping point triggering another, which triggers another, setting off a chain reaction of self-reinforcing changes that would be beyond human control. This is sometimes called a tipping cascade, or hothouse Earth scenario, and while it's considered unlikely at lower levels of warming, it becomes more plausible as temperatures climb. The thresholds for these tipping points are not precisely known. They're among the biggest uncertainties in climate science, but some of them may be closer than we'd like. There's evidence that the Greenland ice sheet and parts of the West Antarctic ice sheet may already be in the early stages of destabilization. The Amazon has experienced increasingly severe droughts. The Atlantic circulation has shown signs of weakening. But here's the thing I want to be careful about, because this part of the story deserves nuance. Climate science is a field that deals in probabilities and ranges, not certainties. The worst-case scenarios are genuinely frightening, but they're not the most likely outcomes. The central projections, the ones that most models converge on, suggest serious, significant, costly changes, but not the end of civilization. The problem with climate change isn't that it's going to end the world next Tuesday. The problem is that it's a slow-moving, cumulative, escalating set of changes that make everything harder: food production, water availability, coastal infrastructure, ecosystem stability, human migration, economic growth, and that the costs of inaction compound over time, decade after decade, generation after generation. So what's actually happening right now? What are the changes we can already observe? The global average surface temperature has risen by about 1.1 to 1.3 degrees Celsius above pre-industrial levels as of the mid-2020s. That might sound small, just over a degree. But a global average is a deceptive number. It's an average over the entire surface of the planet, including the oceans, which warm more slowly. Land areas have warmed more, roughly 1.5 to 2 degrees over pre-industrial levels in many regions. The Arctic has warmed by 3 to 4 degrees or more, and small changes in the global average translate to large changes in extremes. A shift in the average doesn't just mean slightly warmer days. It means the extreme end of the bell curve. The hottest days, the worst heat waves, shifts too, and it shifts more dramatically. Sea levels have risen about 20 centimeters, roughly 8 inches, since 1900, and the rate is accelerating. In the early 20th century, sea level was rising at about 1.3 millimeters per year. By 2006 to 2018, the rate had increased to about 3.7 millimeters per year, and the most recent satellite data suggests it may have accelerated further. The rise comes from two sources: thermal expansion, warmer water, takes up more volume, and the melting of ice from glaciers and ice sheets. Currently, the contributions are roughly equal, but as the ice sheets increasingly destabilize, melting is expected to dominate. Under high-emission scenarios, sea level could rise by half a meter to a meter or more by 2100, and several meters over the centuries that follow. For a world where hundreds of millions of people live within a meter of current sea level, those numbers are transformative. The oceans themselves are changing in ways that go beyond just getting warmer. Remember how the oceans absorb about a quarter of the CO2 we emit? That absorption comes at a cost. When CO2 dissolves in seawater, it forms carbonic acid, which makes the water more acidic. Ocean pH has dropped by about 0.1 units since the pre-industrial era, which corresponds to roughly a 26% increase in acidity. That might sound small, but marine organisms are sensitive to pH changes. Coral reefs, which are built by organisms that construct their skeletons from calcium carbonate, are particularly vulnerable. More acidic water makes it harder for them to build their skeletons, and easier for existing structures to dissolve. Coral reefs support an estimated quarter of all marine species, despite covering less than 1% of the ocean floor. They're among the most biodiverse ecosystems on the planet, and they're in serious trouble. The Great Barrier Reef has experienced multiple mass bleaching events in recent years, where heat-stressed corals expel the symbiotic algae that give them color and provide them with food. If the bleaching is severe enough or happens too frequently, the corals die. And it's not just coral. Ocean warming is shifting where fish species live, disrupting marine food webs and expanding oxygen-depleted dead zones where most marine life can't survive. The base of the ocean food web, tiny photosynthetic organisms called phytoplankton, is affected by warming, acidification, and changes in nutrient availability. These organisms produce roughly half of the world's oxygen, so changes to their abundance and distribution matter far beyond the ocean itself. On land, the impacts are equally broad. Glaciers are retreating almost everywhere on Earth. The Alps, the Andes, the Himalayas, the Rockies, Mount Kilimanjaro. Many smaller glaciers have already disappeared entirely. This matters not just as a visual indicator of warming, but because glaciers serve as natural water towers. They store winter precipitation as ice and release it slowly during summer, providing a reliable water supply for hundreds of millions of people downstream. The Ganges, the Indus, the Yangtze, the Mekong. These rivers are fed partly by glacial melt. As the glaciers shrink, the river's seasonal flow patterns are changing, with potential consequences for agriculture, drinking water, and hydroelectric power across some of the most densely populated regions on Earth. Extreme weather events are becoming more frequent and more intense. This is exactly what you'd expect from basic physics. A warmer atmosphere holds more moisture, about 7% more for every degree Celsius of warming, which is a relationship known as the Clausius-Clapeyron equation. More moisture means heavier rainfall events when it does rain, and also, paradoxically, more intense droughts in between, because higher temperatures increase evaporation. The pattern isn't everything gets wetter or everything gets drier. It's the wet gets wetter and the dry gets drier, and the swings between them get more extreme. Heat waves are becoming hotter, longer, and more frequent. Wildfire seasons are getting longer and more severe, particularly in places like Western North America, Australia, and the Mediterranean, where warmer, drier conditions create more combustible landscapes. And it's not just the direct effects. Climate change acts as a threat multiplier. It takes existing stresses and makes them worse. Water scarcity, food insecurity, disease outbreaks, migration pressures. Climate change amplifies all of them. The World Health Organization estimates that climate change is expected to cause roughly 250,000 additional deaths per year between 2030 and 2050 from malnutrition, malaria, diarrhea, and heat stress alone. And those are conservative estimates that don't account for larger-scale disruptions like crop failures, conflicts over resources, or the displacement of coastal populations. There's also the concept of compound events, when multiple climate-related hazards occur simultaneously or in quick succession. A heat wave combined with a drought, a wildfire followed by a heavy rainstorm on denuded hillsides, triggering mudslides, a coastal storm surge arriving on top of already elevated sea levels. These compound events can be far more damaging than any single hazard alone, and they're exactly the kind of thing that becomes more likely as the climate warms. Now, this is the point in the story where you might be feeling a little heavy, and that's understandable. But I want to shift gears, because the climate story isn't only a story of problems. It's also a story of engineering, of ingenuity, of solutions that are being built and deployed right now, many of them at a speed that would have seemed impossible even a decade ago. And some of these solutions are genuinely extraordinary. Let's talk about solar energy for a minute, because what's happened with solar power over the past 20 years is one of the most remarkable technological and economic stories in modern history. In the year 2000, global solar electricity generation was negligible, a rounding error in the world's energy supply. Solar panels existed, but they were expensive, inefficient, and used mainly for niche applications, like powering remote telecommunications equipment or spacecraft. The cost of generating a kilowatt-hour of electricity from solar panels was well over $1, several times more expensive than coal or natural gas. Nobody in the mainstream energy industry took solar seriously as a large-scale power source. It was a curiosity, a science project. And then something happened. The cost started falling. And it didn't just fall a little. It fell off a cliff. Between 2010 and 2024, the cost of solar photovoltaic electricity dropped by about 90%. 90%. That's not a typo. Solar went from being one of the most expensive sources of electricity to one of the cheapest, in many places the cheapest, in barely more than a decade. In sunny regions, the Middle East, parts of India, Australia, the American Southwest, new solar power plants can generate electricity for 2 to 3 cents per kilowatt hour, which undercuts every fossil fuel. Even in less sunny places, solar is competitive with, or cheaper than, new gas-fired power plants. How did this happen? It's a combination of several things. Manufacturing scale. China, in particular, invested massively in solar panel manufacturing, building enormous factories that drove down costs through sheer volume. Technological improvement. The efficiency of solar cells has steadily improved, with standard commercial panels now converting about 20 to 22% of incoming sunlight into electricity, up from about 15% a decade or two earlier. And learning curves. The more solar panels you build, the better you get at building them. This is a well-known phenomenon in manufacturing, sometimes called Wright's law or the experience curve. Every doubling of cumulative production tends to reduce costs by a relatively fixed percentage. For solar panels, that learning rate has been about 20 to 25%. Every time cumulative production doubles, costs fall by roughly a quarter. And because solar has been growing exponentially, those doublings have been happening fast. Wind power has a similar story, though less dramatic. The cost of onshore wind electricity has dropped by about 70% since 2010. Offshore wind is more expensive, but falling fast. And the turbines themselves have gotten enormous. Modern offshore wind turbines can stand over 250 meters tall, with rotor diameters exceeding 200 meters, each one generating enough power for thousands of homes. The engineering involved in building these things, anchoring them to the seabed or mounting them on floating platforms, and connecting them to the grid via undersea cables, is genuinely impressive. But here's the challenge with solar and wind, and you probably already know what it is. The sun doesn't always shine, and the wind doesn't always blow. They're intermittent, and if you want to run a reliable electricity grid, one that delivers power at 3 in the morning on a calm, cloudy night in January, you need a way to store energy or to fill the gaps. And this is where batteries come in, and the battery story is almost as dramatic as the solar story. Lithium-ion battery costs have dropped by about 97% since 1991, and by about 80% just since 2013. Grid-scale battery storage, which barely existed a decade ago, is now being deployed at scale in places like California, Australia, and Texas. These are enormous installations, shipping containers packed with battery cells that can absorb excess solar and wind power during the day and release it when demand peaks or generation dips. The capacity being installed is growing exponentially. It's not enough yet, far from it. But the trajectory is clear, and it's accelerating. And batteries aren't the only storage option. Pumped hydro storage, where excess electricity is used to pump water uphill into a reservoir and then released through turbines when power is needed, has been around for decades and is still the largest form of grid storage globally. Green hydrogen, hydrogen produced by splitting water using renewable electricity, is emerging as a potential way to store and transport energy on very large scales, particularly for industrial processes and long-distance shipping and aviation, where batteries are too heavy or impractical. The technology is still relatively expensive, but costs are falling. There's also nuclear power, which generates electricity without producing CO2 during operation, and has been quietly providing about 10% of the world's electricity for decades. Nuclear has its own story, its own engineering triumphs and failures, its own political and social complexities, its own safety concerns that are partly rational and partly rooted in a fear of radiation that outweighs the statistical risk. The next generation of nuclear reactors, including small modular reactors and advanced designs that can burn existing nuclear waste, are being developed and in some cases deployed. Whether nuclear will play a major role in decarbonization depends as much on politics and economics as on engineering. And we can't talk about climate solutions without talking about transportation, because getting around accounts for roughly a quarter of global CO2 emissions, and the transformation happening in this sector is remarkable. Electric vehicles were a curiosity a decade ago. Expensive, short-range, slightly eccentric. Now they're the fastest-growing segment of the global automobile market. Battery costs have fallen so dramatically that in many markets, electric cars are approaching price parity with gasoline cars, and the total cost of ownership, including fuel and maintenance, is already lower. An electric motor is simpler than an internal combustion engine. It has far fewer moving parts. It doesn't need oil changes. It converts energy to motion about 3 to 4 times more efficiently. The engineering advantages are overwhelming. The remaining challenges are charging infrastructure, battery supply chains, and the time it takes to turn over the existing fleet of over 1 billion gasoline vehicles on the world's roads. Electrification extends beyond cars. Electric buses are proliferating in cities worldwide. Shenzhen, China, electrified its entire bus fleet of over 16,000 vehicles several years ago. Electric heat pumps are replacing gas boilers in homes across Europe and North America. Electric arc furnaces are producing steel with lower carbon intensity than traditional blast furnaces. The basic strategy is clear. Clean up the electricity supply by switching to renewables and nuclear, and then electrify everything you can. Electricity becomes the universal energy carrier, replacing the direct burning of fossil fuels wherever possible. The sectors that are hardest to electrify, long-distance shipping, aviation, heavy industry like cement and steel, are sometimes called the hard-to-abate sectors, and they account for roughly 1/3 of global emissions. These will likely require a mix of solutions: green hydrogen, sustainable biofuels, carbon capture at industrial facilities, and in some cases, entirely new industrial processes. Cement production alone is responsible for about 8% of global CO2 emissions, partly from the energy used to heat kilns, and partly from the chemical process itself. When you heat limestone to make klinite, the calcium carbonate releases CO2 as a fundamental part of the chemistry. You can capture that CO2, or you can develop alternative cement formulations, but you can't simply electrify the chemical reaction away. These are hard engineering problems, but they're being worked on by thousands of smart people, and progress, while slower than in the electricity sector, is real. Now, there's another part of the solution that gets less attention, but is at least as important as new energy sources, and that's efficiency. The cleanest kilowatt hour is the one you never have to generate. LED lighting uses about 75% less electricity than incandescent bulbs, and think about what that means at scale. Lighting accounts for roughly 15% of global electricity consumption. Switching every light bulb on the planet to LED would save an amount of electricity equivalent to shutting down hundreds of power plants. It's one of those changes that seems trivial on an individual level. You swap a light bulb, big deal. But aggregated across billions of buildings, it's enormous. Modern heat pumps are another game changer, and they're worth understanding because the engineering is genuinely clever. A heat pump doesn't create heat the way a furnace does. Instead, it moves heat from one place to another, using the same thermodynamic cycle as a refrigerator, just running in the direction you want. In winter, it extracts heat from the outside air. Yes, even cold air contains heat energy, as long as it's above absolute zero, which it always is, and pumps it indoors. In summer, it reverses. pulling heat out of your house and dumping it outside. The key insight is that moving heat requires much less energy than creating heat. A heat pump can deliver 3 to 4 units of heat energy for every 1 unit of electrical energy it consumes. That's not magic. It's not violating any laws of thermodynamics. It's just that you're using energy to move heat that already exists, rather than generating it from scratch. The efficiency advantage over a gas furnace, which can at best deliver about 0.95 units of heat per unit of fuel energy, is dramatic. Better insulation, more efficient industrial processes, lighter vehicles, smarter grids. The potential for reducing energy demand through efficiency improvements is enormous, and the economics are often favorable. Efficiency isn't sexy. It doesn't make headlines the way a new solar farm does, but it's one of the most powerful tools we have. And then there's the question of carbon removal, actively pulling CO2 out of the atmosphere. Because even if we reduce emissions dramatically, the CO2 that's already up there is going to stay for a very long time. CO2 doesn't just dissipate after a few years, like some pollutants do. About 40% of a pulse of CO2 emissions will still be in the atmosphere after 100 years. About 20% will still be there after 1,000 years, and a significant fraction will persist for tens of thousands of years. We've committed to a warmer world for millennia, even if we stopped emitting entirely today. So, there's a growing interest in technologies that can actively remove CO2 from the air and store it permanently. The simplest form of carbon removal is planting trees. Trees absorb CO2 through photosynthesis and store the carbon in their wood. Reforestation and afforestation, planting trees where forests have been lost or where they didn't previously exist, are legitimate strategies, and they have significant co-benefits like habitat restoration, soil protection, and flood control. But trees have limits. They grow slowly. They're vulnerable to fire, disease, and drought. And when a tree dies and decomposes or burns, its stored carbon goes right back into the atmosphere. Forests are a temporary reservoir, not a permanent one, unless you're managing them on very long timescales. More ambitious approaches involve technology. Direct air capture, DAC, uses chemical processes to pull CO2 directly out of ambient air. The captured CO2 can then be injected underground into geological formations for permanent storage, or used in industrial processes. There are pilot plants operating right now. The largest, built by a company called Climeworks in Iceland, captures about 4,000 tons of CO2 per year and stores it underground by mineralizing it with basalt rock. That sounds impressive, until you realize that humanity emits about 40 billion tons per year. We'd need to scale direct air capture by roughly a factor of 10 million to offset current emissions, and right now, it costs somewhere around $400 to $600 per ton of CO2 captured, which is far too expensive for large-scale deployment. But costs are expected to fall with scale and innovation, the way they did for solar panels. Whether they'll fall fast enough and far enough is one of the big open questions. There's also bioenergy with carbon capture and storage, BECCS, where you grow biomass that absorbs CO2, burn it for energy, capture the CO2 from the exhaust, and store it underground. In theory, this is carbon negative. You're pulling more CO2 out of the atmosphere than you're putting in. In practice, it requires enormous amounts of land for growing the biomass, competes with food production, and the whole chain of planting, harvesting, transporting, burning, capturing, and storing has to be managed with extreme care to avoid leaks and unintended consequences. And then there's the most controversial area of all, geoengineering. Specifically, solar radiation management, sometimes called solar geoengineering. The idea is deceptively simple. If the planet is warming, because too much solar energy is being trapped. Why not reduce the amount of solar energy coming in? One proposal, which has been discussed seriously in scientific circles for decades, is stratospheric aerosol injection, using aircraft to spray reflective particles, like sulfur dioxide, into the stratosphere. These particles would reflect a small fraction of incoming sunlight back to space, cooling the planet. We know this works in principle because volcanoes do it naturally. When Mount Pinatubo erupted in 1991, it injected about 20 million tons of sulfur dioxide into the stratosphere, and global temperatures dropped by about 0.5 degrees Celsius for the following year or two. But deliberately engineering the global climate in this way raises enormous questions. The effects wouldn't be uniform. Some regions might benefit, while others experience worse droughts or disrupted monsoons. It doesn't address ocean acidification because the CO2 is still accumulating. Once you start, you can't stop. If you ceased the aerosol injection, the full warming that the accumulated CO2 would have caused comes rushing in all at once, a phenomenon sometimes called termination shock. And the governance challenge is staggering. Who decides the global thermostat setting? What happens when one country's preferred temperature is another country's agricultural disaster? There's no global institution with the authority to make that call. This brings us to the political and institutional side of the climate story, and specifically to the Paris Agreement, which was adopted in December 2015 at the 21st Conference of the Parties to the United Nations Framework Convention on Climate Change. And the path to Paris was anything but smooth. The history of international climate negotiations is a long, frustrating story of near misses, failures, and painfully slow progress. The Kyoto Protocol of 1997 committed developed countries to binding emission reduction targets, but the United States never ratified it, and it covered only a fraction of global emissions. The Copenhagen Summit in 2009 was supposed to produce a successor agreement, and collapsed in acrimony and mutual blame. By the time Paris came around, expectations had been deliberately lowered. The negotiators had learned from past failures and adopted a more flexible, bottom-up approach. The Paris Agreement was a landmark because, for the first time, virtually every country in the world committed to taking action on climate change. The central goal is to limit global warming to well below 2 degrees Celsius above pre-industrial levels, with an aspiration to limit it to 1.5 degrees. Each country submitted its own nationally determined contribution, a plan for reducing emissions, and the agreement includes mechanisms for ratcheting up ambition over time, with countries expected to submit more ambitious plans every 5 years. Has it worked? Partially. Emissions have continued to rise since 2015, though the rate of increase has slowed. Many countries have strengthened their targets. The European Union has legally committed to net zero emissions by 2050. China, the world's largest emitter, has pledged carbon neutrality by 2060. The United States has set a target of net zero by 2050 and passed significant climate legislation, including the Inflation Reduction Act of 2022, which directed hundreds of billions of dollars toward clean energy investment. The trajectory of global emissions hasn't bent sharply enough yet to meet the 1.5-degree target. In fact, most analyses suggest that goal is now extremely difficult to achieve. But the world is in a very different place than it was a decade ago. The question is no longer whether we'll transition away from fossil fuels. It's how fast. And that speed matters enormously. Every fraction of a degree of warming matters. The difference between 1.5 and 2 degrees of warming is not just half a degree. It's the difference between losing 70% and 99% of the world's coral reefs. It's the difference between moderate and severe sea level rise. It's the difference between difficult but manageable heat stress and genuinely dangerous heat events in tropical regions where billions of people live. Every ton of CO2 we don't emit makes the future slightly better. Every year of delay makes it slightly worse. There's no cliff edge beyond which all is lost, but there's also no point at which we can say, mission accomplished, and stop. It's a continuum, and every choice moves us along it. Here's something that doesn't get talked about enough when people discuss climate change, and it's the question of fairness. Because the people who are most affected by climate change are, overwhelmingly, not the people who caused it. The countries with the highest historical emissions, the United States, Europe, Japan, and increasingly China, are generally wealthy enough to invest in adaptation, to build seawalls, to develop drought-resistant crops, to air-condition their buildings. The countries most vulnerable to climate impacts, low-lying island nations, equatorial African and South Asian countries, the least developed economies, have contributed almost nothing to the problem. Bangladesh, which is one of the most flood-prone countries on Earth and faces existential threats from sea level rise, is responsible for less than 0.5% of cumulative global CO2 emissions. The injustice is profound, and it's a central tension in international climate negotiations. Developing countries argue, with considerable justification, that wealthy nations should bear the greater burden of emission reductions and should provide financial and technical support for adaptation. The Loss and Damage Fund agreed to at COP27 in 2022 was a step toward acknowledging this, though the amounts pledged so far are small relative to the need. There's also an intergenerational dimension. The greenhouse gases we emit today will affect the climate for centuries to come. The decisions being made right now about energy infrastructure, about land use, about transportation systems, will shape the world that people not yet born will inherit. A coal plant built today will operate for decades, locking in emissions for its entire lifetime. A forest cleared today won't grow back for generations, if it grows back at all. The inertia of the climate system means that the consequences of our current actions unfold on timescales much longer than a single human lifetime. We are making choices on behalf of people who have no voice in the decision. And you know what? Let's step back for a second and think about the arc of this whole story, because it really is extraordinary. A French mathematician in the 1820s notices that the Earth is warmer than it should be and suspects the atmosphere is acting as an insulator. An Irish physicist in 1859 identifies the exact gases responsible through careful laboratory experiments. A Swedish chemist in 1896 calculates by hand how changing CO2 levels would change the temperature and gets remarkably close to the right answer. A British steam engineer in 1938 argues, based on data, that fossil fuel burning is already warming the planet and is politely ignored. An American geochemist in the 1950s shows that the oceans won't save us from rising CO2. A meticulous young scientist starts measuring CO2 from a Hawaiian volcano in 1958 and creates the most important graph in climate science. A Japanese-American meteorologist builds the first rigorous computer models of the greenhouse effect in the 1960s. A NASA scientist testifies before Congress in 1988 that the greenhouse effect is here, and every subsequent decade brings more data, more confirmation, more precision, more urgency. That's over 200 years of scientific investigation, hundreds of scientists, thousands of papers, millions of measurements, and the core conclusion that burning fossil fuels is warming the planet in ways that will have profound consequences for human civilization has only gotten stronger and more certain with each passing year. The science isn't a house of cards. It's a cathedral, built brick by brick over 2 centuries, and every new study adds another brick. Now, I want to end tonight with something that might seem like a small thing, but I think it matters. You know how earlier we talked about Fourier, sitting in Paris in the 1820s, wondering why the Earth was warmer than his calculations predicted? He couldn't have imagined where that question would lead. He couldn't have known that his curiosity about heat would connect, through a chain of brilliant people and careful experiments and painstaking measurements, to the defining challenge of the 21st century. He was just asking how things worked. That's what science is, ultimately. It's organized curiosity. It's people asking questions because they want to understand, and then following the answers wherever they lead, even when the answers are uncomfortable. And the thing about climate is that it's deeply personal, even though it operates at a planetary scale. The air you're breathing right now is the same atmosphere that Fourier was puzzling over 200 years ago. It's the same atmosphere that Tyndall tested in his laboratory, that Keeling measured from his volcano, that every one of us shares. There's no wall between your lungs and the atmosphere. Every breath you take is an exchange with the global system. The carbon you exhale was once in a plant, which pulled it from the air, which got its CO2 from an ocean or a volcano or a decomposing leaf, a chain of transformations stretching back millions of years, running through the same carbon cycle we talked about tonight. And the same atmosphere that keeps you warm tonight, that carries the weather, that scatters blue light to make the sky the color it is, that atmosphere is changing, right now, in response to what we collectively do, not in some abstract, distant way. Right now, the CO2 level in the atmosphere tonight is higher than it was last night, by a tiny, invisible amount. It will be higher again tomorrow night. And the question of what we do about that, how fast we transition to clean energy, how we adapt to the changes already underway, how we balance economic development with environmental protection, how we deal with the deep inequities that climate change exposes. Those are the defining questions of this century, and they're fundamentally engineering questions, scientific questions, human questions. So as you drift off tonight, here's maybe one last thought worth carrying with you. The same curiosity that led Fourier to wonder about the warmth of the Earth, the same meticulousness that led Keeling to count molecules of CO2 from a mountaintop, the same stubbornness that kept Callendar arguing his case when nobody would listen. Those are the qualities that built the understanding we have today. And understanding is power, not in some vague, aspirational way, in a concrete, engineering sense. You can't fix what you don't understand. You can't build a solution until you've diagnosed the problem. And the diagnosis, after 2 centuries of work, is clear. The atmosphere is thin. The greenhouse gases are potent. The carbon cycle is being disrupted. The planet is warming. And the same species that figured all of this out, through stubbornness and brilliance and an extraordinary capacity for sustained intellectual effort, is the only species that can do anything about it. That's either terrifying or hopeful, depending on your mood. Tonight, lying in the dark, maybe let it be hopeful. The solutions exist. The engineering is real. The understanding runs deep. What remains is will and time, and the decisions that billions of individual humans make, day by day, year by year, about how to live on this thin-skinned, warm, improbable planet. And that's a good thought to fall asleep to. Not that everything is fine, because it isn't, but that understanding matters, and effort matters, and the story isn't over. It's very far from over. The atmosphere will still be there when you wake up, doing what it does, cycling carbon, trapping heat, carrying weather, keeping you alive. 4.5 billion years of practice. It's good at its job. Let that settle. Let the ideas drift. And sleep well. The Earth will keep turning, the way it always has, through the long, slow, patient rhythms of a climate that we're only just beginning to truly understand.